In this section, we're going to look at displacement, velocity, and acceleration graphs. The first thing we're asked to do is sketch the following on a position versus time graph. So when are we moving towards the reference point? Well, we're moving towards the reference point when we go towards 0 on the y-axis. So we're moving towards 0 right here on the y-axis. That makes us moving towards the reference point. The blue graph that you see there is coming from a positive position, but we could also do this coming from a negative position right there. So in both of those cases, and those are two ways in which we can move towards the reference point. We can move away from the reference point, so starting at a positive position and move away from the reference point like this, or we can start from a negative position and move away from the reference point like this. Now, it doesn't matter, one is constant velocity and the other one is non-constant velocity. A change in direction means that you have to have some sort of turning point in the s at t function, okay? So what you have to have is you have to have the velocity, which is the slope of the s at t function, equal to 0, and then you have to have a change in the sign of the velocity function. So we'll take a look at this right here. So this would be a change in direction. We have a turning point right here. At this point right here, the velocity is equal to 0. So at this point right here, your velocity, which is your slope of the graph, is equal to 0. And then your velocity, you can see, is going from a positive slope to a negative slope. So you can see that the velocity changes direction. We can also do this on the negative side of the graph, so we can have this right here. So in this case right here, we're moving towards the reference point. We get to a point where we stop, and then we move away from the reference point. If we have a constant velocity, that means that my v at t has to be a constant, and recall that v at t is simply the first derivative of the position time graph. So if the position time graph has to have a constant slope, then we can have this right here. It's linear. Okay, alternatively, we can do it on the negative side, and there we go, that's constant velocity. Now, speeding up while moving towards your reference point, well, that means that the velocity function is non-constant. Okay, and so that means speeding up, it has to get v at t must get larger. So the velocity or the slope of this s at t graph must get larger. And we can see that like this, for example. So we're starting over here and move towards the reference point, and you can see that the slope of the graph gets steeper, which means that the velocity is increasing. We can also do this on the negative side. So we can do, again, moving towards the reference point, and again, seeing that the slope of the graph gets increasingly steeper, slope of the graph being velocity, so therefore your velocity is increasing. Slowing down while moving away from your reference point means that the slope of the graph has to go towards 0. So if we look at this, yep, the slope of the graph is decreasing. Okay. Alternatively, we can do this. We're moving away from the reference point, and the slope of the graph is decreasing. In this section, we're looking at when is the object stopped. So the object is stopped when the velocity function, which is just the first derivative of the position time function, when that is equal to 0. Okay, so we can say that it's starting at rest right here. So the object is stopped at the position right there. So at the starting position, so 0 at B, and from D to E. So if we look like that, there we go. It's at rest there. That's also at rest. Sorry, that meant to be a horizontal line. So as we can see right there, the slope of the first derivative is equal to 0. When does the object change direction? Well, the object changes direction when you have a turning point in the s at t graph. Okay, and so you can see that over here in B, we have a turning point, and we see that our velocity goes from a positive value to 0 to a negative value. Okay, so the slope of the graph goes from positive to 0 to negative, so it's going, velocity is going to the right, then it goes to 0, and then it goes to the left. So we have a change in direction at B. So we'll write that right there. at B. When is the object moving away from the reference point? Well, if we look at the graph right here, moving away from the reference point is when we have it going away from the x-axis, right? So in increasing values of S at t. So at that portion right there, it's going away from the reference point. So we'll say right there, from 0 to B. And then when is the object slowing down? All right, so the object slows down when the slope of the graph goes towards 0. So I'm going to draw some slopes right here. Okay, let's look at from 0 to A. Well, the slopes from 0 to A seem to be getting larger. So 0 to A doesn't work. From A to B, the slopes of the graph seem to be moving towards 0. So from A to B, the object is slowing down. If we look at from B to C, we can see that the slopes of the graph get steeper, so the velocity is increasing. But when we look at from C to D, the slope of the graph is going towards 0. So C to D rather, we also have the object slowing down. From D to E, the object is at rest. And then from E to F, we can see that the slope is increasing, so that the velocity is also increasing. Okay, for the following graph, identify which curve represents the position function, the velocity function, and the acceleration function. Okay, so what I'm going to do here is I'm going to look at this graph number 3. Graph number 3 is a cubic, right there. Graph number 1 is a quadratic. And graph number 2 is linear. Well, if I think about it, S at t to V at t, V at t is just the first derivative of S at t. And if I have a cubic, the first derivative of the cubic is a quadratic. So the cubic is going to be my S at t function, and my quadratic is going to be my V at t function. And recall that A at t is simply the first derivative of the velocity function. So if I look at my velocity function, quadratic, the first derivative of a quadratic is simply linear. So this right here is my acceleration function. Okay, so determine when the object is moving towards the reference point. So when is S at t, so in this case, when is the cubic going towards 0? Well, I'll highlight for you on the graph when the cubic is going towards 0. It goes towards 0 from 0 to 1, from 1 to 2. And then also from 3 to 4, it goes towards 0 as well. So we'll write that right there. So time is an element of 1 to 2 and from 3 to 4. We can also look at this portion right here where it says determine when the object is speeding up. Well, we've previously discussed that an object is speeding up when the velocity function times the acceleration function both are multiplied together are greater than 0. So essentially when V at t and A at t have the same sign. Okay. Positive times a positive makes a positive number. Negative times negative makes a negative number. So let's just focus on when the linear function, A at t, and when the quadratic function have the same sign. So when we look at from 0 to 1, quadratic function is negative, linear function is positive. That doesn't work. When we look from 1 to 2, the velocity function is positive, and the linear function is also positive. So in this case, quadratic function, V at t, and linear function have the same sign. They're both positive. So t is an element of 1 to 2. Let's see if there's another region of the graph in which they both have the same sign. Okay, let's look from 2 to 3. From 2 to 3, the linear function is negative, but from 2 to 3, the quadratic function is positive, so that's not going to work. All right, let's look from 3 to 4. 3 to 4, quadratic function is negative. Linear function is also negative as well. And actually from 3 to infinity is where we have them having the same sign. So I'll say from 3 to infinity. We can also confirm these answers by completing the chart below with the sign table. And so we'll look at s at t from 0 at 1. S at t is your cubic function. From 0 to 1, s at t, the cubic function, is negative. From 1 to 2, so I'll just trace it out for you. From 1 to 2, it's also negative. From 2 all the way to 4, it's positive. But then from 4 to 5, it's negative again. Let's now look at the v at t function. So the v at t function, we can see right here from 0 to 1, the v at t function is negative. But then from 1 all the way to 3, the v at t function is positive. Then from 3 onward, the v at t function is negative. Finally, we're going to look at the a at t function, and we can see that the a at t function is positive from 0 to 2. I'll highlight that. So the a at t function is positive from 0 to 2, and from 2 to infinity, the a at t function is going to be negative. So let's write that in our sign table right here. So from 0 to 2, the a at t function is positive, and then from 2 to 3 onwards, it's negative. And let's just stop and make sure that our values are correct here. So reflecting on the graph that we see above here and the signs that we put into the table, seems to look like we got all of the correct signs. So now what I have to do is I need to confirm when is the object moving towards the reference point. Well, I have to remember that moving toward the reference point means that s at t times v at t, this is moving toward the reference point, s at t times v at t has to be a negative number. So I'm going to use green for this, and I'm going to look, when does s at t and v at t make a negative number? Well, from 0 to 1, right here, if I highlight right here, negative times a negative would make a positive. That doesn't work. Okay. Negative times a positive, that would make a negative number, so from 1 to 2. Okay, from 2 to 3, positive times positive, that makes a positive number, that doesn't work. Okay, and then over here, from 3 to 4, yeah, positive times a negative makes a negative number. Okay, so I'm going to circle this in green right there. This one over here also works. Okay, so then I'm going to write that in also from 3 to 4. And then when we look at 4 to 5, we can see that a negative times a negative will be a positive number. Last one is confirm when it is speeding up. So let's write what happens when it's speeding up. When it's speeding up, we have the velocity function times the acceleration function. As we said before, has to be a positive number. We can see that the intervals over which that's the case is this right here, and then from 3 onward. Okay, so from 1 to 2, and from 3 to infinity. Okay, and the last thing what we have is, this is a graph of s at t, and we have to sketch graphs of v at t and a at t. So the first thing that I want to do is I'm going to sketch a graph at v at t. And v at t looks like this. So v at t is simply the first derivative of s at t. So v at t is just the slope of the s at t function. So if I look from here to here, okay, so from negative infinity, okay, so from negative infinity to that turning point right there, my v at t function has to be a positive number because the slope is positive. Okay, so from negative infinity onward to this turning point, it's going to be a positive number. Right at that turning point, it becomes 0, so I'll put a 0 right there. And then as we move on, okay, the slope becomes negative until we hit this point right here. At that point, the slope is 0. So the v at t function becomes 0, and the slope has to be negative. So from here, between these 2 points, the slope has to be negative. And then as we can see over here, the slope is back to being positive. So from here onwards, the slope is positive. Okay? The other thing that we can see is that since s at t is a cubic, v at t has to be a quadratic because the first derivative of a cubic results in a quadratic. So I'm going to get rid of some of this stuff right here so that it's less confusing. Okay, so I know I have to draw a quadratic that's positive until this point, so I go positive, right? And then I'm going to do a parabola, and then I come back up through there, okay? And so, yeah, so it didn't quite cross where I wanted it to, but you get the idea right there. That's where the velocity function should be equal to 0. Now, if the velocity function is a quadratic, that means that a at t, which is the acceleration function, should be linear. And the acceleration function is simply just the derivative of the quadratic function. So when is the quadratic function? When is the slope of the quadratic function 0? Well, the slope of the quadratic function is 0 right at that point right there. And we can see that the slope of the quadratic function is negative on this side and positive on this side. Okay? So I can go ahead and draw my linear function. Okay? So negative up to this point and positive from here on. Okay, so this is my a at t, and this right here is my v at t, and this black graph right there is my s at t. Okay, so there we have it. Those are graphs of position, velocity, and time. Thanks for watching.